Similarly, as Nicholas Copernicus presented the heliocentric model, another dazzling correction of how we might learn how the universe could form has emerged, starting a discussion known as cosmological emergence. This emergence is set apart by critical disparities in our estimations and comprehension of the fundamental properties of the universe, such as its age, size, and pace of development. Neil deGrasse Tyson has noted that the discovery of the James Webb Space Telescope, JWST, has ended this discussion, an image that challenges material science. So, what exactly is this emergence, and how does the James Webb Space Telescope contribute to it? Well, contributing to it is a bit of a misrepresentation. It's more similar to a survey that has been ongoing. The emergence refers to a point where our interpretation of the universe is challenged, especially regarding its age and size, which are connected by a large safety buffer. The JWST has played a crucial role in this development. Before its launch, our ability to observe the early universe was limited. However, with the JWST's advanced capabilities, experts can now conduct extensive research on distant worlds, providing new perspectives on the universe and re-evaluating past conceptions. This progress enables us to see further into the past, closer to the Big Bang, and observe galaxies as they were forming, offering vital information that can either challenge or support our current universe models. To understand this emergence in detail, it's essential to examine the commonly accepted cosmological model, known as the hot, inflationary Big Bang model or the lambda cold dark matter, lambda CDM model. This model has been highly successful in explaining various components of a universe, from gravitational lensing to the cosmic web structure and galaxy formation. The lambda CDM model posits that the universe began with a Big Bang, followed by a period of rapid expansion, and has continued expanding ever since. It incorporates components like dark matter, which exerts gravitational forces, and dark energy, which drives the universe's accelerated expansion. Despite its success, groundbreaking observations, particularly those made with advanced instruments like the JWST, suggest that the lambda CDM model might be incomplete or in need of updates. For instance, the lambda CDM model predicts that galaxies in the distant past should be smaller, less evolved, and contain fewer heavy elements compared to those we observe in the present universe. This is because heavier elements are formed in stars and dispersed through processes like supernova explosions, which take time to occur. The model also describes the movements of galaxies within groups and clusters, as well as the characteristics of the cosmic microwave background, CMB. According to the model, galaxies farther back in time should appear smaller, less evolved, and poorer in heavy elements. This would imply that, beyond a certain point, we should observe regions of the universe without stars or galaxies. However, researchers have discovered evidence that contradicts these expectations, leading to what is now known as a crisis in cosmology. This crisis centers on uncertainties regarding the universe's age. Different estimation strategies yield varying results, leaving cosmologists struggling to reconcile these disparities. To address this issue, researchers use several methods to determine the universe's age. One approach involves studying the CMB, the remnant radiation from the universe's early days. Detailed maps of the CMB, such as those produced by the European Space Agency's Planck mission, provide crucial information about the universe's composition. However, these maps lack data on dark energy, which constitutes a substantial portion of the current universe. Despite this limitation, researchers use the Friedmann equations, based on Einstein's general theory of relativity, along with other observations to estimate the universe's expansion rate at different points in time and, ultimately, determine its age. By examining the density of components like dark matter, dark energy, and regular matter, researchers can infer the conditions of the early universe and extrapolate its evolution up to the present day. Another method for estimating the universe's age involves observing exploding stars, particularly type Ia supernovae. These supernovae serve as standard candles because their intrinsic brightness is known. By comparing their known luminosity to their observed luminosity, astronomers can determine their distance and, consequently, the universe's expansion rate at different times. This method, used in the 1990s, played a key role in the discovery of dark energy, which is now essential to cosmological calculations. This technique is particularly useful for determining the Hubble constant, a measure of the universe's expansion rate. Although not truly constant, the Hubble constant is crucial for documenting the universe's expansion over approximately 13.8 billion years since the Big Bang. If the universe's expansion is slowing down, it suggests the presence of an unknown force, possibly dark matter, influencing this process. On the other hand, if the expansion rate is accelerating, it implies that dark energy is driving the universe's growth. In January 2018, researchers discovered an intriguing phenomenon. Different telescopes reported varying expansion rates depending on their location of observation. For example, the Hubble Space Telescope observed a more rapid expansion in the nearby universe, while the Planck telescope reported slightly lower measurements in more distant regions. This discrepancy highlights the universe's vastness and serves as a reminder of Edwin Hubble's pioneering work. In 1929, Hubble's observations of distant galaxies revealed that they were moving away from us, demonstrating that the universe is expanding, a discovery that became a cornerstone of modern cosmology. Interestingly, if you were to observe the universe's expansion independently of your local region, you would see the same phenomenon at the same speed. The initial calculations of the Hubble constant were based on limited data. However, with technological advancements like the Gaia and Hubble telescopes, astronomers have been able to observe more variables and refine their measurements. While telescopes use CMB readings to calculate the constant, this method has limitations due to the availability of distant supernovae for observations. Since the discovery of dark energy in the 20th century, researchers have grappled with inconsistencies between different perspectives on the universe's age and expansion rate. As measurement technology improves, even minor variations become more apparent. Although the differences are small, ranging from just 10 to 20 million years, considering that the universe is approximately 13.77 billion years old, these variations still warrant careful examination. One possible reason for these discrepancies is measurement error, though the methods used are among the most precise and extensively tested since the Planck mission's launch in 2009. Another hypothesis suggests a gap in our understanding of dark matter, proposing that it may fluctuate over time or be linked to dark energy or another unknown factor. This possibility has led to numerous experimental investigations. The accuracy of supernova measurements is also under scrutiny, as the complexities of star explosions can introduce uncertainties into the models used. Resolving these uncertainties could help address the disparities in measurements. The discoveries made by the James Webb Space Telescope, JWST, have intensified the cosmological crisis by revealing galaxies and celestial objects that defy predictions based on the lambda cold dark matter, lambda CDM, model. One of the most significant surprises is the detection of galaxies that appear far more mature, massive, and well-structured than expected at such early stages of the universe. These galaxies, observed only a few hundred million years after the Big Bang, challenge the idea that galaxy formation was a slow, gradual process. Instead, their presence suggests that structures formed more quickly than previously thought, raising questions about the fundamental physics that govern the early universe. Moreover, JWST's ability to observe infrared light allows astronomers to peer through cosmic dust and examine regions of space that were previously hidden. This capability has led to the discovery of faint, distant galaxies whose light has traveled for billions of years, offering a glimpse into the universe's infancy. Some of these galaxies exhibit characteristics that are difficult to reconcile with current models, such as unexpectedly high levels of heavy elements that should take longer to form through stellar processes like fusion and supernova explosions. This discrepancy suggests that either stars in the early universe evolved more rapidly than predicted, or that our understanding of star formation and nucleosynthesis requires revision. Another surprising finding involves the large-scale structure of the universe. According to the lambda CDM model, matter should be distributed relatively evenly in the early universe, with small fluctuations eventually growing into galaxies and clusters due to gravitational attraction. However, JWST has detected evidence of unexpectedly large and mature galaxy clusters at epochs when the universe was still young. These observations challenge the timeline predicted by current cosmological models, raising questions about the role of dark matter and the nature of the initial conditions that shaped cosmic structure. This growing body of evidence has led some scientists to propose modifications to the lambda-CDM model. For example, some researchers suggest that dark matter might have properties beyond what is currently understood, allowing it to clump together more rapidly and accelerate galaxy formation. Others explore the possibility that dark energy, which drives the universe's accelerated expansion, may have varied over time, influencing the growth of cosmic structures in ways that current models do not account for. In addition to these theoretical challenges, JWST has also provided new insights into the cosmic microwave background, CMB, the faint radiation left over from the Big Bang. While previous missions like COBE, WMAP, and Planck mapped the CMB in detail, JWST's observations have revealed subtle variations that could hint at previously unknown processes occurring during the universe's earliest moments. For instance, the telescope has detected hints of unexpected temperature fluctuations and polarization patterns that may point to new physics beyond the standard model of cosmology. One particularly intriguing possibility is that the early universe experienced phases of accelerated expansion beyond the initial period of cosmic inflation. These secondary inflationary phases could have altered the distribution of matter and energy, leading to the discrepancies observed in galaxy formation and structure. Alternatively, some scientists propose that the laws of physics themselves may have evolved over time, with fundamental constants like the speed of light or the strength of gravity varying slightly in the early universe. Although highly speculative, such ideas offer potential solutions to the current cosmological crisis and highlight the need for further observational data. As JWST continues its mission, astronomers are using its advanced instruments to test these hypotheses and refine our understanding of the universe's evolution. By studying the spectra of distant galaxies, researchers can analyze the chemical composition and physical conditions of these ancient objects, shedding light on the processes that drove their rapid formation. Additionally, JWST's observations of distant quasars, supermassive black holes at the centers of early galaxies, are helping scientists explore the relationship between black hole growth and galaxy evolution, another area where current models face challenges. Despite these groundbreaking discoveries, the cosmological crisis remains unresolved. The discrepancies between different measurements of the universe's age and expansion rate persist, with no clear consensus on the underlying cause. Some scientists argue that the differences may result from subtle biases or calibration errors in observational data, while others believe they point to fundamental gaps in our understanding of physics. As research continues, it is becoming increasingly clear that solving this crisis may require a paradigm shift in cosmology, potentially leading to a new theoretical framework that can explain both the unexpected observations made by JWST and the long-standing mysteries of dark matter, dark energy, and the universe's accelerated expansion. In this rapidly evolving field, the James Webb Space Telescope stands as a transformative tool, offering unprecedented insights into the cosmos and challenging scientists to rethink their assumptions about the universe's origins and evolution. As future observations reveal even more distant galaxies and probe the earliest moments after the Big Bang, the quest to resolve the cosmological crisis will undoubtedly lead to new discoveries that reshape our understanding of the universe and our place within it. Would you like me to continue further with the implications of these discoveries on theoretical physics, or explore alternative cosmological models that have been proposed in response to the JWST findings? To grasp the scope of the scientific revolution, let's take a look at the origins of the universe. Around 50 million years after the Big Bang, stars, black holes, and star clusters began to emerge, potentially even as soon as 50 to 100 million years later. However, we should expect relatively few incidents. What we don't know is how common galaxies evolved later to encompass events between the Big Bang and 400 million years later. Images from the ongoing JWST reveal galaxies much more distant, and therefore older, than the standard cosmological model predicted. This suggests that our model needs a major update. The discovery that the expanding universe relied on galaxies is a major development. JWST images show galaxies that formed much sooner than anticipated by current cosmological models, causing a crisis in the field. This issue is related to galaxies and redshift, which is a common measurement in cosmology. According to the Standard Model, hydrogen began to appear 400,000 years after the Big Bang, when protons and electrons combined, leading to hydrogen recombination. This changed the universe into a soup of hydrogen atoms, with some helium and residual background radiation. The gravity of the radiation then acted on small fluctuations in this hydrogen gas, slowly pulling them together to lead to the first stars. Early stars were primarily composed of helium and hydrogen, engaged in nuclear fusion, and created heavier substances like carbon and nitrogen. These elements played a crucial role in galaxy formation by absorbing heat and emitting cooling photons, which facilitated the coalescence of gas into galaxies. The process of galaxy formation and evolution is complex and involves many stages. Initially, the gas was primarily hydrogen, but as time went on, heavy elements produced in the cores of stars enriched the gas. This process led to the formation of galaxies that contain not only hydrogen and helium, but also carbon, oxygen, nitrogen, and other elements essential to life. Discoveries, particularly those from the James Webb Space Telescope, have deeply influenced the way scientists view the universe. As researchers continue to explore deeper into space, the ability to observe galaxies and cosmic structures from earlier epochs of the universe challenges many previously held assumptions in cosmology. These observations are not only expanding the horizon of what we can see, but also highlighting discrepancies between predictions made by cosmological models and the data obtained through advanced instruments. This growing body of evidence is forcing cosmologists to revisit old theories and rethink the mechanisms by which the universe is structured. The implications of these new observations are vast. In particular, the JWST has provided illustrations of galaxies that are significantly more mature and evolved than what was previously predicted for their redshift and age. Scientists have been compelled to question the timeline of galaxy formation and the speed at which the universe's structures developed. Under the Lambda CDM model, galaxies were thought to form slowly over billions of years. However, the discovery of galaxies forming as early as 400 million years after the Big Bang suggests that this process could have been much quicker. This unexpected finding indicates that the underlying mechanisms of galaxy formation may be more complex or efficient than previously thought. Moreover, the early appearance of such galaxies complicates the comprehension of cosmic reionization, the time period in the universe's history when the first stars and galaxies emitted enough light to ionize the hydrogen gas that was everywhere in the early universe. The standard cosmological model includes reionization between 400 million and 1 billion years after the Big Bang. The presence of mature galaxies at a much earlier time suggests that reionization may have commenced earlier than anticipated, or that the actual procedure moved more quickly and was more widespread than previously envisioned. These uncertainties could ultimately lead to a revision of our understanding of the nature of dark energy, as well as the cosmic chronology. In addition, the increased ability to study distant galaxies is shedding light on the environments in which these early galaxies formed. Through detailed imaging and spectroscopy, scientists are beginning to understand the conditions of the intergalactic medium and how it influenced the development of galaxies. The interaction between galaxies and the surrounding gas, as well as the way these early structures grouped together, could have played a crucial role in the speed and nature of galaxy formation. By studying these interactions, cosmologists hope to solve the mysteries surrounding the first few 100 million years of the universe's history. In another area of cosmological research, there has been growing interest in the relationship between dark matter and the formation of large-scale structures. While dark matter remains invisible and detectable only through its gravitational effects, its role in the universe's formation is crucial. The gravitational pull of dark matter is thought to have been responsible for guiding the formation of galaxies and galaxy clusters in the early universe. However, the presence of unexpectedly large and mature galaxies challenges the prevailing models of dark matter's influence. Some researchers suggest that dark matter may not behave in the uniform way we have long assumed. It might be subject to fluctuations that account for the accelerated formation of galaxies. The discovery of high-redshift galaxies is also influencing the study of the cosmic microwave background, CMB, a crucial relic of the Big Bang that provides a snapshot of the universe when it was just 380,000 years old. The study of this radiation has already led to significant progress in our understanding of the early universe. However, the emergence of new galaxy populations that fall outside the lambda-CDM model raises questions about the accuracy with which we interpret the CMB. Some scientists have proposed that the CMB may not be as indicative of the early universe as previously thought, but that there might be unknown factors affecting its signature. This possibility would further complicate efforts to refine models of cosmic inflation and the subsequent evolution of the universe. In addition to theoretical questions, these developments present new technological challenges in astronomy. The JWST's ability to observe the faintest and most distant objects in the universe depends on cutting-edge instruments that are constantly pushing the boundaries of what is possible in terms of sensitivity and resolution. As additional data comes in, it is the responsibility of scientists to interpret these findings and reconcile them with existing theories. This requires not only improvements in observational techniques, but also advancements in computational methods to analyze vast amounts of data. The challenges of modeling these results are significant, but essential for ensuring that cosmology continues to progress in an accurate and meaningful way. In summary, the field of cosmology is undergoing a transformative era, largely driven by innovations like the James Webb Space Telescope. These discoveries are forcing a re-examination of long-standing models concerning the universe's history, the nature of galaxies and their formation, and the roles of dark energy and dark matter. With each new observation, the foundations of our understanding are tested, and cosmologists must adapt their theories.